What's good, everybody? It's Jeffrey here with the first ever episode of whatever I'm gonna call this, but I'm here today basically to just teach you about glucose metabolism. It's a topic that I know a lot of my friends don't really understand, so hence why I'm making this video. So anyways, our topic for today is glucose metabolism. And so, with glucose metabolism, we're gonna start off with its first part, which is glycolysis. So glycolysis is basically, to know how glycolysis works, we have to know what goes into glycolysis. And for that, we have our reactants and our products. So for our reactants, we have one glucose molecule, we have two NADH plus molecules, we have two ADP molecules, and two phosphates. And at the end of glycolysis, we'll have two pyruvates, two ATP, and two NADH molecules. So let's get started and I'll show you how each of these reactants and products go into glycolysis. So first off, naturally we start off with glucose, and then we get two ATP molecules that come in and hydrolyze and become two ADP molecules. So these two phosphates that were lost by ATP then attach to the glucose molecule, which now becomes known as fructose 1,6-biphosphate. And because the phosphate heads of these molecules are inherently negative, enzymes come in to break this carbon molecule at the 3 and 4 carbon sites, creating two separate molecules of glyceraldehyde 3-phosphate. And keep in mind that if you want to impress somebody, you should remember these two names, fructose 1,6-biphosphate and glyceraldehyde 3-phosphate. Okay, so moving on, we have these two glyceraldehyde molecules, and an enzyme brings another phosphate to both of these molecules, now attaching to both of their sides, then creating some molecule that our professor doesn't want us to remember, so I'm not going to bother you with the details. So anyways, these molecules are then met with an NAD molecule, and an NAD molecule is basically an electron carrier. So the NAD takes away two electrons from this molecule to create NADH, and so we have and then two ATP molecules come in to take away the two phosphates that are on this 3-carbon molecule and create two ATP. Make sense? And then what we're left with at the very end is two pyruvate molecules. Moving on, we have to keep in mind that after glycolysis occurs inside the cytosol of a cell, and it can either go two paths. It can either go in anaerobic metabolism or aerobic respiration. Anaerobic metabolism is where only happens if there is a lack of oxygen present in the cell, and aerobic respiration happens with there is oxygen present in the cell. So for simplicity's sake, we'll start off with anaerobic metabolism because it is the easier of the two. So yeah. So to understand anaerobic metabolism, we have two cycles. We have lactate fermentation and the Cori cycle. Lactate fermentation is basically when a pyruvate created by glycolysis is then turned into a lactate molecule, and this lactate molecule is brought into the Cori cycle to be used, and I'll show you how it's used. So the most typical version of the Cori cycle can be seen in your muscle cells. So your muscle cells use glucose, goes through the whole process of glycolysis, and creates pyruvate molecules. And these pyruvate molecules are then converted into lactate molecules. And with these lactate molecules, you cannot have a high buildup of lactate molecules inside your muscle cells because it causes a pH imbalance. So the muscle cells then secrete this lactate into your blood and brings it over to the liver. And within your liver, the lactate can then be transformed into pyruvate molecules, and now the liver can go through a process called gluconeogenesis. And through gluconeogenesis, it uses 6 ATP molecules to create one glucose molecule that can then be turned back through the whole cycle and brought back to the muscle cells. But there's a caveat to this. Because of the use of 6 ATP molecules, this process cannot be sustained for very long, and your liver will not be able to keep up with the demand that that the glucose puts on it if there is a high demand for glucose. And the second process that we talked about earlier is aerobic respiration, which by the name aerobic is where there's a presence of oxygen within the cell. So through aerobic respiration, I'm going to show you guys an image, and it's going to look pretty complicated, but I'll try to break it down as easily as I can for you guys so you can understand. So we have this image, which should look pretty familiar because it's pretty much from my notes. Like all the images I have are from my notes. But anyways, so we start off with the glucose molecule, and this glucose molecule is then, through glycolysis, keep in mind, is made into 2 pyruvates, right here, 2 pyruvates. So with these, and also through glycolysis, 2 NADH molecules are created, and also 2 ATP was created. So with these 2 pyruvates alone can't go in to the Krebs cycle. So they have to be converted to acetyl groups. So these, to be converted to acetyl groups, it's 2 NADH molecules are secreted as well as 2 carbon dioxide are created. And this creates an acetyl group. And this acetyl group is then picked up by a CoA enzyme, thus the name acetyl-CoA. And as you can see, through the Krebs cycle, what we get from it is 4 carbon dioxide, 6 NADH, and 2 FADH2, as well as 2 ATP. And all these NADH and FADH2, I'll explain what happens to them later on in the video, but for now we'll talk about the Krebs cycle. So we'll be talking about the Krebs cycle. Okay, so the Krebs cycle is kind of complicated, but not really. As long as you know how to follow this chart pretty much, you'll be golden. But so anyways, we start off with an oxoalate molecule right here. So the oxoalate molecule is then met up with the acetyl-CoA molecule. So the CoA molecule drops off the acetyl group on the oxoalate molecule, creating citrate. And remember, we have to know, for the test, we have to know acetyl-CoA, oxoalate, and citrate. And thank God she doesn't make us remember all the other names of these molecules, because I don't even know what they are, and I doubt you guys want to be bothered with all those details, so I'm not going to spend time to talk about it. Anyways, since the oxoalate becomes citrate, it now goes through the cycle. So the first part is an NAD plus molecule comes in and takes away electrons from the citrate molecule, creating NADH. And at the same time, a carbon molecule is also taken away from the citrate molecule and binds with the oxygen that's already present within the cell, because keep in mind, this is aerobic respiration, and so there should be oxygen present in the cell. So with the loss of this carbon, it now becomes a 5-carbon molecule that you don't need to know the name of. And with this 5-carbon molecule, another NAD molecule comes in and takes away more electrons and becomes NADH. And at the same time, a carbon is broken off and binds with O2, the same way as I said earlier. So now we have a 4-carbon molecule. And with this 4-carbon molecule, as it goes through the cycle, another molecule comes in called GDP. This GDP molecule phosphorylizes with a phosphate that's floating around somewhere and becomes GTP. And this phosphorylation from GDP to GTP also gives energy for ADP to bind to bind with the phosphate to create ATP. And that's why GDP converts to GTP. And as we go down the cycle, we have FAD. So FAD is very similar to NAD+. And the FAD basically comes in and takes electrons from this 4-carbon molecule to create FADH2, which is another carbon, like I said, it's an electron carrier. And then we have another NAD molecule that comes in and takes away more electrons to become NADH. Okay, so after all of that, our final products of the Krebs cycle are as follows. We have 6 NADH molecules, 2 FADH2 molecules, 2 oxoalate molecules, 4 CO2, and 2 ATP. The reason why these are our numbers are because within the Krebs cycle is always ran through twice, because 2 pyruvate molecules were created through glycolysis, meaning there's 2 acetyl-CoAs. So with 2 acetyl-CoAs, the Krebs cycle was ran through twice, pretty much. And now, since we've done the song and dance with pyruvates, what do we have left? Well, like I mentioned earlier, what we have left are the 10 NADH molecules and 2 FADH2 molecules. And these come from the Krebs cycle glycolysis and when the pyruvates were turned into lactate. No, not lactate. These come from when the pyruvates were turned to acetyl groups. And so these NADH and FADH2 molecules are then brought into what is called the electron transport chain. So, electron transport chain is, I admit, kind of complicated, but trust me, when I explain it, I'm pretty sure you'll get it a lot better than what you did before. So, electron transport chain occurs in the cristae of the mitochondria. Much like the Krebs cycle also takes place inside the mitochondria. So, yeah, now I'll show you how electron transport chain works. And the picture I'm about to show you is not the best, I'll admit. I could have drawn this a lot better, but I just hope you take my words and yeah, I'm sure you have a better picture in your notes, but anyways, here is what the electron transport chain sorta kinda looks like. It's a mess, I know, but I'll try to break it down. We have these NADH and FADH2 molecules, and they come in and they give the electron transport chain their electrons. They drop them off. But keep in mind that these NADH molecules also drop off hydrogens because they've been carrying them every time that they took away an electron. They also take away hydrogens with them. So these NADH molecules drop off their electrons, and as these electrons go through the electron transport chain, it creates an electrochemical gradient. And all of the hydrogens that are in the matrix, which is basically the inside of the mitochondria, and the matrix, because of this electrochemical gradient, the H plus ions are allowed to cross the membrane. And so once these H plus ions cross the membrane, they are brought to the intermembrane space. And within the intermembrane space, because of this buildup of hydrogen ions, it creates potential energy. And with all these H plus ions, they don't want to be together because, as you know, like repels like. So the only way they can go back down their concentration gradient is through the ATP synthase, which I'll show you in greater detail. So with the greater buildup of the H plus ions, these H plus ions then want to go down the ATP synthase to go down their concentration gradient. But as it does this, the potential energy of the H plus ions are then converted to kinetic energy, which is traveled straight down to the ATP synthase, where inside the ATP synthase, that the change from potential to kinetic energy allows ADP to phosphorylize with the phosphate and become ATP. So basically ATP synthase is basically is what makes the most amount of ATP within the glucose metabolism loop. And as these H plus ions go down the ATP synthase, they can be met with an oxygen atom that is present because, remember, this is still aerobic respiration. So these H plus ions bind to the oxygen and can create water, H2O. And so, anyways, the ATP synthase then creates a net amount of 32 ATP. And I guess that's pretty much it. I went through glycolysis, anaerobic metabolism, and aerobic respiration, as well as the electron transport chain. If you guys have any more questions, you should hit me up if you need anything else. But anyways, thanks so much for watching, and I hope you guys do well on your tests soon. And I don't know, I might do more of these videos down the road if I feel like it, because I admit this is pretty fun. But anyways, thanks for watching, and I'll see you all later.